Hi. So we're going to continue our discussion of the circulatory system with a review on blood vessels. Just big picture here. What is it that we're trying to learn? We're trying to evaluate what is the physiology that, goes into delivering blood flow to each muscle group, right? We breathe in oxygen and we want to carry this oxygen into blood, and we want to know how that process happens and how is it that then it is pushed into each vessel and then it is carried into each muscle, tissue, and organ, and then how is it that that blood goes back into the heart. So understanding blood vessels will allow you with this physiology. Now, why is it important to know it? Because in order to understand the pathology of each organ, each system, you need to understand how it was functioning well to begin with. So you need to know the physiology of the system, a normal physiology, and then the pathophysiology will come into play later as you move into your career. This is going to be a go over. This is going to be a review of the entire chapter in blood vessels. So to start with, know the general direction of blood. We start at the heart and then we go in through elastic arteries, muscular, resistant arteries, and then we get to the arterioles. And as we get to the arterioles, then we go to the capillaries, and in the capillaries is where we unload all of our fuel. We pick up all of that waste, and then we start making our way back into the heart through venules and then veins, and then back to the heart. All right. The general structure of these blood vessels that carry the blood are with three layers. Arteries and veins have three layers. So remember the three layers are the tunica intima, the tunica media, and the tunica externa. It's only three of them. The main differences among them are is that the tunica intima is just the inner thin layer of endothelial lining, made out of simple squamous epithelial cells. All right, so it is basically this is a the inside. We're gonna have simple squamous epithelial cells making out the outer ring of that the tunica intima. Out the outside of that, then we have the tunica media. The tunica media is going to be concentric muscle sheets. All right, so it is concentric muscle sheets. What are the differences between veins and arteries? Well, in arteries, this layer is thicker, okay, because they need to squeeze. The tunica externa is the one that comes next, and this one is thicker in veins than it is compared to the tunica media. All right. So three layers: tunica intima, tunica media, and tunica externa. Something else to remember is that there are going to be two layers, two elastic layers: the internal and the external layer in arteries. The internal is in between the tunica intima and the tunica media, and the external elastic membrane is going to be between the tunica media and the tunica externa. And this is what provides some of that elasticity to the arteries. So again, key characteristics of the arteries, it is that they are muscular, so they have strength, and they're muscular because that tunica media is media is thicker. It has a lot of that smooth muscle, and it also has elastic membranes. So this is what provides that elasticity. Now we're asking the internal elastic membrane is separating the tunica intima from the tunica media. So we have the tunica intima, and we're going to put in here the tunica media. In between those, we're going to have a small band of elasticity. Now the tunica externa is going to be in between the tunica media and the tunica externa. So we'll just put another ring right here, and then we'll put the tunica externa outside. All right. If, if smooth muscle cells in the tunica media of an artery relax, what happens to the lumen of an artery? When we're talking about the lumen, it is the inside of the vessel. So this is the vessel itself, and this is space from here to here. This is what we call the lumen. All right. So if we narrow, if we constrict, if we go from here to here, if we constrict that vessel, the lumen will decrease. All right, and this constriction, the constriction of the vessel, happens because that tunica media, which has a smooth muscle, is starting to contract, and when it starts to contract, well, it reduces the lumen of the vessel itself. This is happening through sympathetic activation. The decrease of that sympathetic activation, we are not sending signals to the vessel anymore to increase vasoconstriction. It will lead to the relaxation, that pressure, that vessel, because we have blood going through it, right? This is blood, and this blood is pressurized. The vessel will return back. All right, the blood inside has pressure, and that pressure is what is pushing the vessel's blood back, and we don't have that resistance anymore from those concentric muscle sheets to push it in, because there is no activation. So to answer your question, if a smooth muscle cells in the tunica media of the artery relax, what happens to the lumen? It increases. Know the differences between arteries and veins when viewing vessels under a microscope after a sectioning. So as we just saw, if we have a vessel under a normal state, then we cause vasoconstriction. We have released molecules to cause vasoconstriction. The lumen has decreased. Actually, let's make it more apparent. The lumen has decreased. You can see how from here to here, now it's gotten smaller because of that vasoconstriction from that smooth muscle cell, from that tunica media. Now, when we cause vasodilation, there is no more activation of those muscle cells, so the pressure inside of that artery is going to relax, and it's going to go back to that normal state. All right, because there is pressure inside of blood. But when we do a cross section in the microscope, there is no more blood, there is no more pressure. So let's see, once the patient is dead, okay, so once we're taking just a cross section, or let's put in here, once no more blood inside, and that is either the patient is dead or you just took a cross section, regardless of the patient's status. But the idea is that that vessel is not in vivo anymore. All right, and when it is not in vivo anymore, the lumen will contract, will decrease, because there is no more blood pressure inside to push it out. However, why does it go back? Is there activation of that muscle sheet? No, there is no activation of that tunica media. However, remember that you have in arteries a elastic membrane in the internal side, so internal elastic membrane in between the internal tunica intima and the tunica media, and you have an outer external elastic membrane in between the tunica media and the tunica externa. All right, so it is that elastic membrane that will show you arteries as if they were smaller. Let's take a look at the next picture. Here you can see the artery under the microscope. You can see that the artery seems smaller. That is because it doesn't have the blood to push it out, to push it wider. It's not that it's under construction. This is the inner layer. This right here is the tunica media. And then outside of it, we have the tunica externa. Comparing that to veins, the veins, you can see that they don't have as much of that tunica media. They have a thin tunica media as opposed to arteries. They don't have the elastic membranes either. However, the tunica externa is a lot thicker compared to their tunica media. It's not to say that the tunica externa is thicker than it is compared to the tunica media of arteries. We're comparing it to itself, all right? So in arteries, usually round and relatively thick wall because of that tunica media. The tunica intima is endothelium made out of smooth muscle cells. We can see that it is ripple. They are saying that it's ripple right here because the lumen has increased. There is an internal elastic membrane that is present. That tunica media, it has thick, smooth muscle concentric sheets, and it also has an external elastic membrane. The tunica external, again, is just collagen fibers, connective tissue. Veins. The veins, the tunica externa is larger than its tunica media. The tunica media of veins is thin compared to the arteries because it doesn't need to constrict. The elastic membrane the internal, external elastic membranes are not present. They're absent. All right. The endothelium that runs inside veins is usually smooth, and that is because there is no constriction. The lumen inside is expanded most of the time. Cells of the tunica media and tunica externa receive nutrients and oxygen from what? So as you continue to picture those three layers of vessel, okay, the tunica intima, the tunica media, which is all that muscle, and the tunica externa, which is the connective layer. You can see that blood here, the blood cells that are in here are carrying nutrients. So they may provide nutrients to this first portion right here through diffusion. But as we go into the outer portion of the vessel, how do we feed it? Because all of this tissue is alive. It has to renew, it has to supply. So diffusion can only get you that so far. So there are blood vessels that run along the vessel and they pierce that wall and they feed that vessel itself. And that is what we call the vasa vasorum. Okay, small arteries and veins that supply blood to the tunica media and the tunica externa. Which group of vessels are considered contractile, muscular, and elastic? So here we're going to talk about arteries to begin with. So as we take a look at blood flow progression, we start with arteries. And arteries has different types. We're going to start with the first one, and that is elastic. Then we have muscular, and then we have arterials. And blood flow goes from top to bottom. So the first type of vessel to encounter blood is going to be the elastic artery. And that is because we have our heart pump, and we need the vessel to be very elastic to withstand the pressure and allow that recoil to even out the pressure and propel and continue that pressure through so that it can communicate it down into the vessel. This is what we call pulse force. But let's go back a little bit. What are the main characteristics of elastic arteries? That they have more elastic fibers as opposed to and fewer muscle cells. Okay, they have more elastic fibers as opposed to either muscular or arterials. We're talking about two specific vessels and those are the ones that are connected just outside of the heart, and that is the pulmonary trunk and the aorta. This elasticity allows the heart to withstand the large pressures that is going through here, and as it is pushing out, because it has those elastic fibers, it will snap back, allowing the pressure to continue throughout that vessel. And that is what we call pulse force. Next is the muscular arteries. Once we're past those large vessels, we're going into this medium-sized artery. And this is what we call the distribution arteries. These are important because this is where we see most of vasoconstriction and vasodilation happening. These types of vessels have a large muscular tunica media. So when we cause vasoconstriction, we're affecting mostly muscular arteries. And once we get into the periphery or into the organ or the tissue that we need to perfuse, then we go into arterioles, which are the smallest of the arteries. And in our progression, okay, let's go ahead and let me go ahead and erase this. In our progression, we have elastic, we have muscular, and we have arterioles. So the elastic, it has more of the elastic layers. The muscular has more of the muscular layer. And the arterial, instead, it has lost layers. It has lost layers, so it's very, very thin. It's starting to lose some of that tunica externa, little to no tunica externa. It has a very thin to incomplete tunica media. So it is mostly tunica intima. It's mostly endothelium. The arterial diameter can change according to local conditions and sympathetic activation or stimulation. The outer, because the lumen has decreased so much, the lumen, remember, the inside of that vessel is so small, even though we have very little to none of that tunica media, just a little bit of contraction can reduce significantly that lumen, increasing resistance within that vessel. Resistance, remember, that is what is opposing flow. All right, so as we have flow to a vessel, we have blood, we have red blood cells moving through. If we make that vessel thinner and thinner and thinner, the blood flow is going to decrease because there is more resistance. The vessels are closing in on that cell right there. So when we cause vasoconstriction, when we narrow that lumen, that cell is slowed down, it backs everything up. So these constricted arteries oppose blood flow, creating resistance. Arterioles are resistance vessels and they regulate blood flow. So if you back this up right here at the end, it's gonna back everything up. All right, so that is what we call that a resistance vessel. That is what we call afterload. And is usually referred as to that total peripheral resistance. But again, there is more resistance as we cause vasoconstriction, and these vessels, because they are very small, are called also the resistance vessels. Now that we went into detail about the layers of a vessel and we know the normal structure of them, what if there is something wrong? There is a weak spot in the vessel itself. All right, well, because there is pressure in here that is trying to push, the blood is pressurized as it is carried through. If there is a weak spot, it's gonna make this bulge. All right, it's gonna make a bulge, and that is what we call an aneurysm. Now this bulging is problematic because it can, for one, rupture, and if it ruptures, all that blood is gonna rush out, and that is what we call a hemorrhage. The second problem that can occur from this is that it may compress surrounding tissues. So if you are in the brain, everything is pretty tight. So if you're pressing on a section of the brain, then you may be affecting this portion, this section of the brain. That's that. Okay, this is just a quick summary of the progression of the vessels. We go from elastic arteries. You should know which vessels are those. Then we go into muscular arteries, which are the ones that are most affected by, sympathetic activation and parasympathetic activation. Then we go into arterioles, our resistance vessels, and you should know that this blood flow is affected the most here. Then we go into our capillary. Remember that there are multiple types of capillaries. Here we're dropping nutrients, and then we're picking up waste, and then we're bringing them back to the heart, and we're trying to get rid of all that CO2. Now we're going to the larger veins, and then we dump it into that superior vena cava, inferior vena cava, and the heart is also dumping into from the coronary sinus. Next, what type of capillary has pores? It's endothelial lining. What does it allow to enter or leave the blood? So we went through the natural progression of blood through the arteries, the differences among them, and the layers. Now let's talk about capillaries. So there are different types of capillaries. Remember that we have continuous, we have fenestrated, and we have sinusoid. Okay, so we're gonna start with one of them. This question in particular is referring to one that has pores, and the one that has pores is going to be the fenestrated. Okay, so this type of capillary has pores in its endothelial lining. What does it allow to enter or leave the blood? So the capillaries are basically a vessel that just has a very thin endothelial lining. Remember that the arteriole had lost all of its membranes by the time it went into the arteriole. Now, when it gets into the capillary, it's just endothelial lining. All right, it's just that tunica intima. Now, these cells in between the connections in the continuous capillary, we have tight junctions right here that allow the exchange of nutrients through diffusion and some specialized channels. So that is how we bring in and we exchange nutrients, gases, they naturally diffuse. However, because of these junctions right here, we cannot release proteins. So plasma proteins stay in here. Blood cells stay in here. What about medications or medium-sized molecules? Well, it depends. There is a type of continuous capillary that is specialized that we call the brain-blood barrier. In the brain-blood barrier, these junctions are more complete, so they are tighter, and we definitely don't allow anything to cross or enter unless it is through active passage. In regular continuous capillaries, remember that we don't have all of those complete junctions. Sorry, let me just erase this. But we have the tight junction. We have a tight junction, but in between we still have a cleft. Okay, those cleft here allow for passage of specific molecules. All right, also through diffusion. How is this different than fenestrated? Well, fenestrated is going to have pores. All right. So we have our endothelial lining, and these pores have like channels that allow the same size molecules to enter and leave very rapidly. So these pores in the endothelial lining are like holes in the cells. Okay, through. It doesn't have to be in between, it can be through. They permit rapid exchange of large molecules. Where do you think that we need this? The kidneys. Because we're trying to filtrate all that waste out, so it needs to be fast. We use it also in endocrine organs and the intestine throughout the GI tract, and that is because we need to pick up nutrients. This type of capillary allows the exchange of large substances like plasma proteins and blood cells. So we talked about continuous capillaries, fenestrated capillaries, which is a faster form of the continuous because it has those pores in between. Now the sinusoids have holes in between. So we have our endothelium. Let's go ahead and make it like this. But we have a full crack right here, allowing molecules as big of a cell to enter in and out. That is how we have a red blood cell production enter the systemic circuit. In our bone marrow, we're producing cells, right? If we had continuous capillaries, we wouldn't be able to, allow red blood cells to enter into circulation. But here we allow for that leukocytes and myelocytes. Actually, no, those are in development. So erythroblast and mature red blood cells enter in circulation at this stage, red blood cells. There is going to be also macrophages within specific organs such as the liver, spleen, and bone marrow that are also helping recycle red blood cells. So in the bone marrow, the macrophage is going in, picking up, destroying in and out of this. And it kind of lives in this sinusoid capillary. These are big gaps in between the endothelial cells. All right. This wouldn't work in the periphery. It has to be on specific locations. And that is because if you had large gaps in the periphery, you will have a leakage of plasma proteins into the periphery, and that will cause a lot of issues. Another type of molecule that you should keep in mind here that is entering systemic is plasma proteins. The liver is producing plasma proteins and it is allowing them to enter through one of these big gaps right here. It's like a huge hole. Endocrine organs also have, hormones that need to dump in there. Okay. The spleen, we're recycling those red blood cells. So how can we allow red blood cell recycling to happen? Well, through one of those holes. Just keep in mind, liver secretes plasma proteins to the sinusoids. Macrophages enter in and out to recycle red blood cells. These allow free exchange of water and large proteins between blood and interstitial fluid. Which type of capillary allows for the exchange of the respiratory gases, oxygen and carbon dioxide? Think of how they cross in and out of the blood. This is just going back to continuous capillaries. We have our endothelial lining. We have some tight junctions. But we also have, and we'll put another cell over here. But we have clefts. We have like openings that allow blood through here, but these openings are very small. These are in between the cells. And this is a complete endothelial lining, okay? Most in active tissues, except the epithelium and the cartilage, all right? They permit the diffusion of water, solutes, lipid soluble. So the lipid soluble go across the cell. The the small solutes have to go in between that cleft. They do not allow plasma proteins, large molecules, or blood cells to live in and out because they have the tight junctions. This is different again than the fenestrated, because the fenestrated has something that we call what? Pores. And these pores are like channels through the cell that allow for rapid exchange of those solutes. In and out, in and out. But again, are we allowing large molecules to live in and out? No. It's just enough. It's just as big as the cleft, of the continuous capillary. This is just a quick picture to sediment this knowledge. We have continuous, all right. We have our lumen, we have our cells, and we have some tight junctions, but we also have clefts. Okay, these clefts, like openings, allow for the exchange. Now the fenestrated, so this is continuous, this is the fenestrated. We also have clefts, we have tight junctions, but now we have pores in between. You can see that they're about the same size, and this allows rapid exchange. You know the organs, and those are kidneys. What is another one? GI. And what is another one? I'll let you write that one down. Now the last one, it is going to be the sinusoids. These ones are found where? In the liver, in the bone marrow. Another one, spleen, and I'll let you write the last one. But the idea is that we're allowing large proteins through these huge gaps right here, in and out, in and out. The liver is dumping plasma proteins. The bone marrow is allowing the red blood cells in and out of that circulation, and that is how we allow new red blood cells or cells in general to enter circulation. What does the spleen do? How does the spleen utilize the sinusoids? I'll let you uh, complete that one. All right. So we went through the arteries, the types of vessels of the arteries, and we head into the capillaries. In the capillaries, we saw that there are different types of capillaries depending on the tissue that we're trying to supply with, with nutrients. Within the capillary itself, there are some physiological changes that can happen as a reaction to a stimuli. So for instance, with vasomotion. Vasomotion is the idea that we're shunting blood from one section of the capillary bed to another section of the capillary bed, and that is where it is needed. We have a capillary bed right here. We're gonna picture that the arterial feeding this capillary bed, and we have like up to 10 of them. Okay. This is the capillary bed, but we're exercising and we're using more of the muscle fibers on this section. Sorry, let's go ahead and make it in blue. The muscle fibers on this group right here are being utilized the most. These ones, the muscle fibers that are being supplied down here, are resting, are at rest. So with vasomotion, we start to constrict this capillary bed, this portion, okay, at the beginning, so that that way the blood flow that is coming through here is coming more so, is supplying this bed, so that this muscle group that was working out, that was being contracted more, that was being utilized, receives more supply. All right. So vasomotion is related to that contraction and relaxation of the precapillary sphincters that allow shunting of blood. This is controlled locally and chemically by these soft gas concentrations. So when we start working out, we start consuming oxygen. So the capillary bed is going to have a decrease in oxygen. and an increase in CO2 because that muscle group is consuming more energy, and as we are using more energy, we're producing more CO2. So that is going to cause vasodilation or relaxation of that precapillary sphincter. Now, that in contrast to this one, then this one will have a rich supply of oxygen and a decreased CO2. So that is what is causing that vasoconstriction right here, that contraction of those precapillary sphincters. So we have precapillary sphincters and collaterals. Let's take a look at that at this. So you can see the precapillary sphincters. These are the precapillary sphincters right here. If we want blood flow to go into this portion, into this muscle that is being supplied, then we're gonna constrict these ones right here, so we can allow that blood flow to go here instead. All right. Know the terms. Arteriovenous anastomosis is the junction between an arterial and a venule, or an artery and a vein. We have our precapillary sphincters. We have collateral arteries, which means we have vessels, different vessels, supplying a capillary bed that is of the same type. And then we have veins and venules. Dash are capacitance vessels know about the relative distribution of blood volume, the response to blood loss. So here they're talking about arteries or veins. Which ones are, oh, well, I guess I'm telling you right here. Okay, so we're gonna put in here veins. Veins are capacitance vessels. Know about the relative distribution of blood volume, the response to blood loss. About 2/3 of blood at all times, of your body is in veins. All right. So if you start bleeding out, if the person starts gushing blood out, all right, they cut their arm off and it is gushing, then that means that your heart and your internal vital organs are going to have a loss in pressure because there is less blood going through your systemic circuit. So what does the body do? The body has blood going through that venous system. Is going to contract it, and it's going to shunt more blood into that arterial system. Okay, and that is what we call the vasomotor centers of stimuli sympathetic nerves. There is a venous response. There is venoconstriction. All right. Oftentimes it is happening to redistribute the venous reserve, where we have very bloody organs such as the spleen, that it has a lot of blood, so we can constrict that and rush that blood into the arterial system. This picture kind of puts it into perspective. So we have large veins, okay? We have a large network such as in the liver, bone marrow, and skin, and we have another medium-sized veins. As you can see, they make up most of the blood as opposed to the arterial system. But if there is a leakage here in this arterial system because it is highly pressurized, your vital organs need the oxygen, then we're gonna cause venoconstriction, and that venoconstriction is gonna bring more blood to the system so that we can redistribute blood. Does venoconstriction happen at all times? No, it happens during blood loss. So just keep in mind the physiology and the response in physiology when there is a specific stimuli. Okay, so capillary blood flow is proportional to pressure over resistance. So flow, Let's just write it down. Flow equals pressure over resistance, and this is, we will say, kind of like it is to the fourth power. What happens to flow if we change either pressure or resistance? So in this equation, if we have flow that is equal to pressure over resistance, if we increase pressure, we're gonna increase flow. All right, and let's write it again. If we increase resistance, we're going to decrease flow. All right. However, because this resistance is to the fourth power, any changes in resistance is going to significantly affect flow. Okay. So when we increase pressure and resistance, we usually just focus on resistance. The cardiovascular system proportional to pressure. What is proportional to pressure? Increasing pressure will increase flow. So flow is proportional to pressure, and that means that F is proportional to pressure. Now resistance, flow is inversely proportional to resistance. So flow is inversely proportional to resistance. All right, and that decreases flow. Increasing resistance decreases flow. So although flow is proportional to pressure, resistance is the big game changer here because it is to the fourth power. So changes on that vessel lumen are gonna significantly decrease or increase flow to where you want it to be. All right. What variables affect total peripheral resistance? So remember that total peripheral resistance is the entire resistance of the cardiovascular system. So we're talking about capillaries, we're talking about arteries, we're talking about veins. You know how we talk about the lumen inside of the vessel, how there are red blood cells that are going through, but as we narrow that vessel, those red blood cells, we're gonna have to start slowing down because we're cramming them into a smaller one. All right. So what affects total peripheral resistance? One is going to be vascular resistance. Okay, how narrow those vessels are. Also, if you have more red blood cells, well, your traffic jam is going to be even bigger. So that is what we refer about blood viscosity. All right, how thick that blood is. And we have turbulence. Turbulence means they are relating to the vessel or the structure where blood is going to. Let's go ahead and erase this just for a minute. So flow in a vessel that is nice and smooth is going to be faster. These red blood cells right here are flowing really fast. But if the insides of this vessel are all gunked with atherosclerotic plaques, like you are eating junk, so then these red blood cells are going like oop, 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 oop. So it's going to be slower. So there is more turbulence right here. Turbulence. Okay, so quick summary. We're trying to deliver blood to the organs. The heart is pressurizing this blood and it's trying to overcome afterload. All right, all that pressure within that arterial system. So, but all that pressure is referred to total peripheral resistance. All right, and that total peripheral resistance, the three characteristics are vascular resistance, so the size of the vessel, viscosity, how thick that blood is, and the medium by which they are traveling. If it is all gunked out and there is a lot of turbulence, it's going to slow down that, and it's going to make it harder for your heart to pump against those pressures. Resistance to flow, caused by molecule and suspended materials in the liquid. Whole blood viscosity is about 5 times that of water. We cannot know that. General stable anemia, polycythemia may affect viscosity. Yes, because if you have more red blood cells within polycythemia, that is going to increase it. If you have anemia, that is going to decrease it. That's correct. We have a swirling action that distributes a smooth flow of a liquid, generally stable, unless we have atherosclerotic plaques. This is just a visual of what is happening within the vessels. Here we have the vessels. We have elastic arteries, muscular, arterioles. We're going through our progression. We have now capillaries, venules, veins, and then we go back to the heart. Okay. Now the cross-sectional area means how many of those vessels are. So if you were to grab all of your vessels and cut them in half and add that cross-sectional area, you will see that this is the cross-sectional area measured in centimeters. There is not that much of the elastic arteries. I mean, they are large and they carry a lot of blood flow, but there is not that much of it. And then there is more capillaries in cross-sectional area throughout your body. As you remember, the capillaries are very, very small. So what happens? Well, because they're very, very small, blood flow decreases. Because as blood starts to go into those capillaries, we start cramming it down, and we need to slow it down because we also want exchange to happen. But so you know, the cross-sectional area of capillaries is much larger in the body. All right. And with that is what we call it, the resistance vessel as well. The blood flow into those capillaries is decreased. All right. Pressure and resistance. So just key concepts to keep in mind here. When we measure blood pressure, we talk about like in a patient with his arm with a sphygmomanometer, we're measuring the arterial pressure. All right, we're not measuring venous pressure. The pressure in the venous system is very low, but we're focusing on the pressure of that left ventricle because we're focusing about a blood flow, oxygenated blood flow. This is measured. We have two peak pressures. We have systolic pressure, which is the peak pressure during ventricular systole, and we have diastole, the minimum pressure during ventricular diastole. So when you look at the blood pressure of a patient, you're going to have X number over X number usually. Okay, systolic such and such and diastolic such and such. Just know that this is the minimum arterial pressure during ventricular diastole. All right. How is this important? Because as we are pushing more blood, as we increase that pressure, all right, if we were to combine it, we will get a mean arterial pressure. So let's just use this just for a second. The mean arterial pressure is what we're trying to use as we are trying to calculate how much of that blood we're pressurizing against capillaries, because we want to filter it out. We want to allow this to diffuse out all these nutrients, not the red blood cells, unless we're in a sinusoid, right? But we're trying to diffuse all of that oxygen, carbon dioxide, so that capillary hydrostatic pressure is referring to the force within the capillary beds. So that force that is pushing out all of that at the beginning of that arterial, a capillary bed coming up from an arterial. Okay. Now the venous pressure, it is just much lower. All right, because all of that pressure has been utilized. So we've used all that kinetic energy. When we talk about arterial blood pressure, know what is normal, know what is abnormal, with either hypertension, so abnormally high blood pressure greater than 130 over 180. There are different categories of that. We're not going to get into hypertension pathology. However, just know what will be abnormal. And hypotension will be abnormally low blood pressure, all right? Which will be below this value. Actually, no, below. Do we have? I don't know if we have one. I don't see it. But abnormally low blood pressure. So if you were to see 60 over 30, that would be incredibly low or incredibly high. Normal is this is 120 over 80, so this would be really low, and we call it hypotension. Pressure and resistance. So we have another just a few concepts as we go back into that discussion of a blood pressure. We have pulse pressure, which is the difference between systolic pressure and diastolic pressure, and this is to represent the force of the heart contraction. We have mean arterial pressure. Within mean arterial pressure, we're using this so that we can have just one pressure itself. I think my pen battery went out. Oh no, here it is. Okay. Single pressure blood value to give us a reference. So you are not, so as you calculate some of the physiological changes, it may be easier to just deal with mean arterial pressure. So going back, total peripheral resistance is affected by multiple things, and that is resistance or vascular resistance, which is changes in lumen. We have viscosity, which is affected by anemia, polycythemia, the amount of red blood cells or solids within that vessel. And we have last. Okay, I'm gonna let you figure that one out. Make sure you look it up and make sure how is it that it affects total peripheral resistance. Okay, so this is related to this one, to atherosclerosis. So atherosclerosis, it is making it so that it's not as smooth. All right. Oh, here it is. Wow. I didn't. I thought I was gonna make you guys look it up. Okay, so we have blood flow, and it is making it more turbulent. So that is not as smooth. So it is increasing some of that force that the heart is having to push against. How is atherosclerosis affect total peripheral resistance? If we have a more atherosclerosis in the body, we are increasing total peripheral resistance. So that means that your heart is working harder, okay, to push against that total peripheral resistance. Describe how velocity, speed of blood flow changes throughout the systemic circuit. How do vessel diameter and cross-sectional affect it? You remember how we talked about that little graph where we're looking from arteries and we have veins as we progress, and we can see that there is less of the large arteries, muscular arteries, and then we have a huge cross-sectional area of the capillaries, and there is a lot of them. Now, because these are very small vessels, as blood is flowing, we have another graph that measures flow. The flow is decreased significantly here, and that is important because it allows for exchange. So cross-sectional area, as it increases, it decreases flow. All right. So how does diameter cross-sectional affect it? And as it decreases cross-sectional area, either in the venules or the arteries, we increase flow again. Here is higher, here is higher. This is another picture to show vessel in diameter. The diameter of the elastic arteries is huge, but there are not as many of them. We have the vessel diameter of the veins, and we don't have that many of them. We have more of that cross-sectional area of arteries. So just keep in mind that even though capillary size is very small, okay, the actual vessel itself, because there is so many of them, because so many of them throughout your body, is that we have a large cross-sectional area. Cross-sectional area is just measuring the size from here to here, the size from here to here, from here, 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 here. So, but because there is just so many of them throughout your body, that size ends up being so much larger. Now, arteries, even though they are bigger in diameter, they are larger vessels, there is only fewer of them. So the space from here to here may be larger, however, the cross-sectional area is less compared to that of capillaries because we just have so many more of them. Okay. Remember that elastic arteries, we have two, pulmonary trunk and a aorta. Now within the capillaries, we have capillaries to the vein. We have capillaries one to the, well, yeah, within the vessels themselves. We have within the spleen, the bone marrow, every tissue that you think of needs a blood supply. So there is a capillary bed in there. How does blood pressure change throughout the systemic circuit? So we have our heart, our pump that is pushing out of that left ventricle and is pushing out, and that pressure is greatest in the elastic arteries, and it starts to distribute that, that pressure. It starts to decrease, decrease. So pressure throughout the system decreases. So if pressure decreases, how is it that we have more, how can we get blood back to the heart? Now the venous system is assisted. We have is assisted through a couple of methods, all right? And that is muscular compression, the respiratory pump. So assisted means that there are other physiological processes that are helping the blood go back. As you can see, this muscle, when you squeeze it, it allows for the blood to be pushed here. These one-way valves, what they're allowing is they're preventing blood from rushing back, right? Because there is a low pressure, this is preventing blood from rushing back. So whenever we squeeze it, we open it, and we go onto this one. And then when that muscular compression is not happening anymore, well, we're going back to low pressure. So then they will close back up. So we have one-way valves that open to allow passage of blood flow but prevent backflow. What is that respiratory pump? The respiratory pump has to do with pressures into the intrathoracic cavity. So when we inhale, we're pushing that diaphragm down, okay? What is squeezing the diaphragm, and what is happening to the intrathoracic cavity? It is expanding. So when we expand the cavity, do we increase or decrease pressure? Think of how we bring air in. We have to decrease pressure in order to bring air in, and because we're doing that, we're decreasing the pressure, we're sucking blood in. So when we're taking a deep breath in, we're bringing blood, the venous return is being enhanced to go back to the heart. And when we exhale, we're allowing the recall of that diaphragm. Now that could be either through passive or active muscle groups. But when we exhale, we're increasing the pressure, and that allows that actually prevents the return of blood flow. But it's with that inhalation that we're allowing the blood to run back in. So just wanted to go over a couple key concepts which are vital to homeostasis as we are working through the capillaries and we're trying to exchange materials. So we have diffusion, filtration. Diffusion means that we're moving molecules from a high concentration into a low concentration. All right, this is important because as we are bringing in oxygen, these areas are, they're not rich in oxygen. They have poor oxygen, but they are rich in CO2. So once the muscle fibers have consumed that oxygen, they release all that CO2. So all that CO2 that is being concentrated and is being produced by muscles, tissues, these ones do now diffuse into circulation, into arterial circulation, because when we look at the arteries, we have rich oxygen, and that rich oxygen wants to diffuse here. All right, some of these forces play into rate. Now, filtration. Filtration, it applies to the removal of solids as a solution driven across a porous membrane. So when we talk about the capillaries, remember that we have an arteriole, and the arteriole is feeding multiple capillaries. The force that is carried through this arteriole is then communicated into each one of these capillary vessels, the capillary bed. All right. The higher the pressure it is continued, the higher the hydrostatic pressure, so the more solutes are going to be filtered out, right? Because yes, we have more pressure into each one of those vessels, so it is going out into the interstitial fluid, right? Now later into the capillary, we're going to have some solutes. Let's go ahead and make those purple. Flow back in as we go now into venules. Okay, so and that brings us to reabsorption. So just those three concepts: diffusion, filtration, and reabsorption. What primary factor drives filtration during capillary exchange? Filtration drives fluids and solutes from a high concentration to a low concentration. And remember that the pressure that is used for filtration, so we have the arterial, we have the capillary bed. Actually, let's make it red so that it doesn't look at it like it's in veins. So we have an arterial that we are feeding that capillary bed, and the pressure that is inside here is distributed to each one of these vessels, and it is this pressure inside that what we call hydrostatic pressure, and that is what is pushing the solutes out into the interstitial fluid. Remember that in order to get those solutes into the cells, we have now tissue cells over here. The solutes go into the interstitial fluid, and from the interstitial fluid get into the cell for the nutrients. Now the waste will go into the interstitial, will go out into the interstitial fluid, and then those will be collected at the end of the capillary bed and then be collected into venules. So hydrostatic pressure is the physical force liquid against the surface. It pushes water from an area of high pressure to an area of low pressure. That brings us to reabsorption. Reabsorption is primarily driven by what force? And reabsorption moves fluid solutes from and to. So reabsorption's primarily force utilized is osmosis. And in osmosis, we're moving solutes from high concentration to low concentration. Now, how does the vessel bring back the fluid? So we have, let's go ahead and paint our capillary. So we have our arteriole feeding all these the capillary bed, and we're gonna say that this is when they become, and this is a venule now. So venule, we have an arteriole, we have the interstitial fluid, and we're gonna paint a couple actual cells throughout. Okay, so we have proteins within. So we have plasma proteins, we have red blood cells, so we have the red blood cells, we have some of these proteins. So these proteins in a continuous and fenestrated capillary, they do not go into the interstitial fluid, they stay here regardless. So these red blood cells do not go into the interstitial fluid, right? They stay within the capillary and they collect in the venule. And the same for the plasma proteins. And all these large molecules stay within the vessels themselves. And because there were a lot of solutes, let's go ahead and put them in green. There were a solute. The solutes did diffuse. Okay, we had oxygen going into the interstitial fluid, then into the cell. And out of the cell, we now have CO2. And that diffuses in here, and now we have CO2 in here. Okay. And there were other solutes, ions, that were diffusing to the interstitial fluid. We were filtering a lot more solutes. We filter out a lot more into the interstitial fluid than we suck back in. But the way we're sucking it back in, or like bringing it back in, is with something that is called blood colloid osmotic pressure. So there is a higher concentration now within the venule, since we filter out a lot of those nutrients and we have now large proteins, red blood cells. It is very concentrated, and we pushed out a lot of water as well. Okay, then we're going to have some of that be reabsorbed by osmosis back into that venule. Right, not all of it, but some of it. Key concepts on this process: that this reabsorption, this blood colloid osmotic pressure, is driven by blood proteins, plasma proteins that are not filtered out. And that is because we have a capillary, and we're talking about capillaries such as the continuous and the fenestrated. So now the next question is, what causes edema and what is edema? Remember how we have our capillary bed? Actually, let's color code it. We have our capillary bed with all of our arteries, and now we have the deoxygenated portion of it, and we have now a venule. We have an arterial. And we're talking about what type of capillary? We're talking about the most common, which are the continuous and the fenestrated. And we have our capillary here. Outside of that capillary bed, we have the interstitial fluid, and we have cells. The actual tissue that we are supplying. The actual tissue that we are supplying, that exchange of nutrients, of oxygen, happens at the tissue level through the capillary bed. It doesn't happen from the arterial or the venule. It happens at the capillary bed. We have red blood cells rich in oxygen. So we're just gonna put here. We have plasma proteins. We have water. Okay, we have a lot of it, right? I mean, remember what is in blood. We have formed elements, and we have plasma. All of that is going through here. So we filter out most of the plasma, so nutrients, but we're gonna keep all the plasma proteins within, because the openings are not big enough. We don't have sinusoid capillaries. All right, so the plasma proteins. But as we lose water and solutes at the first portion of the capillary, okay, the first portion of the capillary will filter it out into the interstitial fluid so that it can get inside the cells. This portion right here, the latter portion of the capillary, becomes more concentrated. So we have more of a colloid pressure, okay? So that blood colloid pressure will force through osmosis that return of fluid back into the latter portion of the capillary, that then is collected into the venules. And we also have the red blood cells. Okay, now that they are deoxygenated. All right, they're deoxygenated. How do we calculate the amount of solution that went out of that capillary? We have the net hydrostatic pressure. And into this net hydrostatic pressure, we have two main components. So what is the net hydrostatic pressure? The net hydrostatic pressure is the net filtering out of the molecule. So we have the capillary hydrostatic pressure, which is the pressure pushing out, CHP. We're gonna put it here, CHP is pushing out, is what is pushing out all of that plasma, of that, like all the water, all the solutes. We have that CHP, and we have the interstitial hydrostatic pressure. The interstitial fluid also has pressure, and that is pushing against, that is pushing out, that is pushing back into the capillary bed. Let's put it here. There is some pressure within. Okay. Because of our hydrostatic pressure is higher, your capillary hydrostatic pressure is higher, we push more out of capillaries than we suck back in, and that is higher than the interstitial fluid is pushing back in. The net filtration pressure can be calculated as follows. We have the capillary hydrostatic pressure, so how much is coming out. We're just gonna put this as blue. How much is coming out of that vessel. Let's just paint a vessel right here. This is a capillary vessel. The interstitial hydrostatic pressure is pushing it back in, but it's small. That is smaller. Minus, we have the blood colloid. So the blood colloid pressure is pushing it in or out. It's pushing pressure inside of the vessel. And the interstitial colloid osmotic pressure, that is pushing it out. That is pushing it out. Overall, the forces that capillary hydrostatic pressure is oftentimes bigger than what we have here. So overall, we have more filtration. We're filtrating more materials out than we're bringing back in. Okay, so the forces are greater going into that capillary than they are exerted back onto it. Now, some of that fluid that was lost, some of that water, some of those solutes will end up going back through the lymphatics. Because if we continue to lose, volume, all right, water through these capillaries, then what is going to happen? We're not going to have any blood to return to the not the formed elements, but actual volume, actual plasma, actual water to go back into those venules. So in order to maintain that volume, what we're going to do is we're going to collect the extra interstitial fluid or extra water through the lymphatics and dump it back later on into the venous system. All right, so just key concepts. We have net hydrostatic pressure, we have net filtration pressure. All right. If we now, to answer the question, what causes edema or what is edema? Edema just means that there is more interstitial fluid that can be reabsorbed through the lymphatics, right? You can imagine still that there is more. Let's go ahead and clear this out for a second. Okay, I cannot clear it out. Oh, yeah. Just took a second. Okay, so the idea is that if we had cells, again surrounded by interstitial fluid, and we have our capillary vessel. All right, if we have too much going into it, too much water, there is going to be a collection of water and, plasma into this interstitial fluid. So that is what causes edema. There is going to be a swelling in that interstitium, right? And it could happen either through increased circulatory pressure, starvation, and you can imagine that it happens through starvation because now the liver is not making plasma proteins, so the blood colloid pressure, or the pressure that is used to suck back in or bring back in all of that water, all those proteins that are here, there are less of them. So if we have less of them, then there is going to be more of that fluid that stays behind into the interstitial fluid. That is how starvation increases edema and tissue damage. If you were to affect the capillary bed, if you were to injure it, you still have the arterial feeding all this pressure down to here. So you are going to continue to filter it out. Another tissue that can be damaged is the lymphatic. Let's assume that the capillary bed is intact, all right, that the capillary bed is intact, but the lymphatic tissue that is supposed to pick up the excess water in here, that this is damaged. There are lymph nodes, right? Now, if this type of tissue is damaged, well, there won't be reabsorption, so there will be a collection of edema in that tissue itself. This picture shows it a lot better than what I was drawing. However, the key concepts remain. We have the arterial feeding into this capillary bed. All right. We have the net filtration pressure, which means that we have capillary hydrostatic pressure. So the pressure that is coming in, hydrostatic pressure, so which is this one, is 35. Let's assume it's 35. But the blood colloid pressure is driven by all those proteins, plasma proteins. So all the plasma proteins that are in here, plasma proteins, PP, is making it so that it's bringing this back in, and that is through osmosis. There is more solutes in here than there is into the interstitial fluid with all the cells out here. However, there is more the pressure that where the net filtration pressure is higher, so then there is going to be more fluid going out of that capillary than is being reabsorbed back in. You can see it right here. Reabsorption is a lot smaller, so we have 10 minus 7, we have plus 3 still coming out. That extra plus 3 is going to be sucked back in from the lymphatics. All right. During capillary exchange, the capillaries filter more fluid than they reabsorb, and the excess fluid is reabsorbed through the lymphatic vessels. So let me just again picture my capillary bed. Arterioles, venules, capillary. We're filtering out 24 liters, and we are reabsorbing through that blood colloid pressure about 20 liters, so 24, and so about 3.6 liters that are into the interstitial fluid, all right, are going to be taken back in by lymphatic vessels. If the lymphatic vessels are damaged, what happens? Edema. If the pressure, if there is more pressure coming in, that a capillary hydrostatic pressure increases, so your systemic pressure increases, what happens? We have edema. All right. Just as a recap, what factors act as local vasodilators? Remember that we have that capillary bed, and the capillary bed, when we're talking about vasomotion, may want to redirect and shunt blood flow to this section as opposed to this section. So we do this through a constriction and relaxation of sphincters in that capillary bed. So you will say that you will want to vasodilate if you want to increase. Yes, so you want to dilate when you want to increase flow in tissues. Okay, so we're gonna, this section right here will dilate because we want more of this. How do we dilate it? With chemical factors, with local vasodilators. Will you say that if we have more oxygen in this section, we will vasodilate or will vasoconstrict? So oxygen will be a local vasoconstrictor, and CO2 will be a vasodilator. All right, and that is because if the muscle cell or the tissue that is here is consuming, you are working it out, and is consuming more oxygen, the byproduct is going to be CO2. So it is releasing a lot of CO2 into this section. So that capillary beds know, hey, look, this tissue needs more blood flow. So we need to relax to allow more flow into this section. And we do this through CO2. So CO2 is a vasodilator, oxygen is a vasoconstrictor. Cardiovascular regulation. When tissue perfusion, and we're talking about blood flow to tissues, is inadequate, there are three levels of regulation that can alter blood flow to correct the issue. That is autoregulation, neural regulation, and hormonal regulation. So we have this when the perfusion that can be affected to three regulatory fashions, the regulatory elements: autoregulation, neuronal, and endocrine. So within autoregulation, we talked about local local molecules that are released to cause the precapillary sphincters to constrict or relax. If they constrict, they shunt blood away. If they relax, they increase flow. All right. So what are those molecules that affect the constriction and relaxation of those precapillary sphincters? Well, when we have low oxygen and high CO2, that means that the tissue is consuming more oxygen and releasing more CO2. So the precapillary sphincter is going to relax, as well as low level. Know these three. These are the three elements that will allow the precapillary sphincter to relax so that there is more blood flow to be taken there, as well as a nitric oxide. So we have four: low O2, high CO2, and there's going to be low pH, and nitric oxide. Local vasoconstrictors. So if we have the opposite happen, if we have more oxygen, then there will be a release of thromboxanes. These are released by activated platelets so that there is less blood flow to that section of the capillary. So what are the local vasoconstrictors? Thromboxanes. And local vasoconstrictors constrict precapillary sphincters. I guess I could have written it here. Thromboxanes released by activated platelets, and we have precapillary sphincters. Another question is, which type of receptors monitor arterial blood flow for hypoxia or low oxygen, or hypercapnia, high CO2, pH, for pressure? So whenever we're talking about chemical changes such as oxygen, CO2 changes, pH changes, we have chemoreceptors. Whenever we have a change in pressure, we are talking about baroreceptors. If we have a decrease in pressure, remember that flow equals pressure over resistance. If we have a decrease in pressure, we're decreasing proportionally flow. So in our heart, if we have a decrease in pressure, then baroreceptors are going, or let's talk about specific baroreceptors that are within vessels themselves, and we're talking about the carotid baroreceptors. If there is a decrease in pressure, this is going to stimulate a sympathetic response so that we can then increase tonicity to those vessels, and we can redistribute blood to the brain or to the heart. So we have three ways in which we can redistribute blood flow: at a local level, through autoregulation. So we can release molecules such as CO2, oxygen, pH. These ones can cause a vasodilation if we have an increase, decrease, decrease, increase. All right, and we can constrict some of those capillaries through thromboxanes. All right, and this is because we want to redistribute blood flow. Local factors cause immediate localized adjustments in blood flow by dilating or constricting precapillary sphincters. Local vasodilators are compounds that cause precapillary sphincters to relax in order to increase blood flow to a specific part of a tissue. Four things act as local vasodilators. Boom, right here, remember those. Local vasoconstrictors are compounds that cause capillary sphincters to contract in order to decrease. While compounds, boom. Now let's go on to another form of regulation, and that is neural regulation. So the vasomotor center in the brain has sympathetic neurons that adjust vessel diameter in order to adjust blood pressure and blood flow to large areas of the body to ensure blood pressure composition is homeostatic. So remember that we have sympathetic responses where we're releasing epinephrine, norepinephrine. And when we increase these, we are affecting mostly that tunica media, which is made out of largely smooth muscle. So when we activated the receptors within that smooth muscle, what do? We contract or relax. We vasoconstrict. So an increased output of the vasomotor center means sympathetic neurons release epinephrine, norepinephrine onto a smooth muscle in the vessel walls. This causes muscle to contract. Now there is not a molecule that makes it so that it opens up. It's just a decrease of the epinephrine and the norepinephrine that allows that the pressure on that vessel to open back up. So a decrease in sympathetic output, a decreased output from the vasomotor center means that the neurons release less. Okay, so I guess that they wanted up here release more. I thought they were trying to list it out. Less norepinephrine to smooth muscle in the vessels, which causes relaxation. Okay, and if we relax, there is an increase in vessel lumen. We're gonna go ahead and pause here because this has been about an hour and 30 minutes. I want you to go back and review what we've done. and I'm gonna continue the next portion of this review in another video.